After I took a class with him, the way that I always describe the way he teaches is that he never says anything that doesn't make sense. Everything he says just makes sense the first time he says it.
Let's say there's a student who's like, I'm locked in. Do you have any tips for that kind of student?
Yeah, go into it hard. I always prefer when students come to me and want to do projects for credits, I always prefer that they come up with a project idea because I think it's really important as you work on projects that you're passionate about. If you ever find yourself preparing for an interview or trying to build your resume, add something to your project portfolio, and you're not passionate about what you're doing, like you're not passionate about the skills that you're gaining to put on your resume or the project that you're building, then maybe you're looking at the wrong company. There's 1,000 other applicants that are applying for the same job, and one of them is going to be really qualified. One of them is going to be the student who joined all the clubs, they did all the hackathons, they did all the coding competitions. You want to be that student if you can.
What's up, guys? Welcome back to the BeaverHacks Podcast. I'm your host, Havel Konda, and today I'm joined by Alex Guyer. He's a computer science professor at OSU. He's done research on various machine learning topics, especially those related to computer vision, and he's teaching a lot of the introductory level computer science courses here. And I'm really excited to get to know him, and thanks for coming on the show.
Yeah, happy to be here. Thanks for having me.
Awesome. So, we had Engineering 103. That's the class that I had you with. Kayla was in the class as well, and I'd say it was a really good experience. Probably one of my best introductory spaces for getting into this world of programming with C++.
That's high praise.
Yeah.
Thank you.
But before we dive into like how you teach and like that whole process, what really got you into computer science in the first place?
I don't know if there was like one incident. I've always just like kind of been drawn to computers. I guess when I was growing up, I used to play a lot of video games, and I guess looking back, like in my lifetime, I've kind of got to watch things like really evolve very quickly over time. Like I used to play like everything from like Legend of Zelda Ocarina of Time,
yes,
to Legend of Zelda Tears of the Kingdom. Like I played all of them and everything in between. And so I've got to see like the way that computers have evolved and hardware has evolved and algorithms have evolved and the new kinds of things that you can do with it. And just watching that evolution was always like very inspiring. It was always so cool to see what people can do with computers now that they didn't used to be able to do 5 years ago, and imagine what we'll be able to do with them in another 5 years,
I got to ask, Breath of the Wild or Tears of the Kingdom?
I don't know. I like them both. They're both very good.
They're both great games,
yeah.
Honestly. But yeah, it's crazy to think about how, like, with the Breath of the Wild game, that was like one of my first Zelda games.
Oh, really?
I was never into the originals, but to see the evolution from like Breath of the Wild to Tears of the Kingdom, just within like how many years was it? It was like 2017.
Yeah, too many.
Too many years, but the level of difference in that just really highlighted these advancements in technology.
Yeah, it's pretty astounding.
You did a lot of research in machine learning and AI as well.
Yeah. So, I guess I was interested in it even way back in high school. I think when I was in robotics, I heard the word neural network from my friend, and that kind of set everything off. We didn't use neural networks in high school robotics, of course. I wish we could have, but it's not like we had the budget for anything like that.
Right.
But yeah, I definitely I found an early interest in it. I self-studied a lot. And then when I did my undergrad here at OSU, we didn't have like AI degrees and AI tracks or even micro-credentials for AI or anything like that back then. So I did computer science was my major, applied CS. And then my focus was, I think it was like a custom focus, but it was like AI driven. And then eventually I did my master's degree. We'll talk about my thesis later.
Okay, yeah. Awesome, yeah. I think I'm doing something like that now too, where it's like, I'm trying to go with like a custom AI data science combined. Lots of math, but honestly, yeah, it's kind of what comes with it.
Yeah, especially like linear algebra, very important. Statistics, I think not enough people who study AI take statistics very seriously, but it's just statistics. So
why do you think that is?
I don't know. There's probably historical reasons for it.
Yeah.
AI is it's kind of a buzzword at this point. So is
right.
machine learning. They're all just a bunch of buzzwords. But the reality is that machine learning is basically just like applied computational statistics, but it's a different camp of people. Like the people who study machine learning don't call themselves statisticians.
Right.
The people who study statistics don't call themselves AI practitioners or anything like that. But we're really doing the same thing.
Right.
So yeah, I definitely think people who study AI should take statistics seriously.
In terms of, your research, were there like any projects over the years that you like really felt stood out in terms of what you did?
Yeah, so in my master's program here at OSU, I took theory of computation with Mike Rosalek, and the final project was we had to pick a problem that was like an NP hard problem of some sort, and then reduce it to like a PSAT problem, and then feed it into like a PSAT solver to solve the problem. And at the time, I mean, it was in my master's program, so I was working on my thesis, and my thesis was related to AI. And so I talked with my advisor, Tom Dietrich. I was like, do you have any ideas for like maybe problems in AI that we could treat this as an NP hard problem? We could reduce it to a PSAT problem. And he's like, I don't know, maybe there's something in like decision trees or something like that. And like a theory of like building decision trees, like how we train decision trees. I mean, there are ways that we train them, but in theory, maybe there's an algorithm where you can like construct some sort of optimal decision tree under some definition of optimality. And so I did some research, and I found that there are ways to treat like constructing like a depth minimal decision tree or a smallest decision tree for a certain problem that achieves like total separation and classification or something like that. That's like an NP hard problem. And so I spent the next couple of weeks working with my partner on the project, Jared Hollis. He's still, I think he's still a PhD student here at OSU. But we worked on this together, and we did it. Like we sat down, we figured out how to like translate this problem of like constructing a depth minimal decision tree and translating it into a PSAT problem, feeding it into a PSAT solver. I think we just implemented it all in Python. And it was very cool, like by the very end. And like, I don't know how practical it is to make a depth minimal decision tree. Like it's probably not super practical, but it was still very cool in retrospect. Like this was like a real problem that I could actually solve applying the techniques that I just learned in this course. It was very interesting. I think that's, looking back, that was maybe the project that I did. It was a very short project, but I was still kind of proud of myself at the end of being able to accomplish it. It's pretty cool.
On that note, taking these like theoretical concepts and then turning them into practical applications that can be used to solve problems in the real world. What's your stance on that, and how that kind of affects your motivation? Yeah,
I definitely am a problem solver. Like that's why I like computer science. Is I just like solving problems, and they don't even, as you can probably guess, they don't even necessarily have to be practical problems. They just have to be interesting, I guess. And so I definitely think a lot of times there's a big gap and it depends on how the education is done, how the instruction is done. But there can easily be a gap between what's taught in the classroom and like how to apply it in the real world. And so I always think it's really important when I'm teaching, for example, to try to make that gap as small as possible. And so, for example, when I teach, I like to teach like almost entirely by demonstration. I don't like to stand up there with like a slide deck. And you can do that. You can teach out of a slide, and you can do that effectively. But I personally just really like to make that gap as small as possible. That way, if I expect students to be able to apply this knowledge in a certain way to solve a certain kind of problem, the way that I want to teach that knowledge is by showing them how to solve those kinds of problems. And yeah, I think that's maybe where we can improve in really just in education in general. I mean, there are entire schools where like their entire teaching paradigm is like entirely just like hands-on, let's solve problems together. And I think that's really important.
Sort of a show, not tell.
Yeah, exactly. Show, not tell.
Awesome, yeah. Was there like a particular professor that kind of inspired you to kind of take this route? Or was this sort of like I saw professors maybe not doing this, and then I wanted to take this route?
No, I've had lots of good role models over the years. I mean, a lot of the professors that I had are still here because I was a student not that long ago. I'm still very young. I mean, for example, Rob Hess.
Right.
He's going on leave soon. He and his wife are having babies. Okay, but he was like my favorite professor, or my favorite instructor. When I was in undergrad, and I think I basically just totally adopted his teaching style, and like I guess I can just try to mimic him. Like looking back, what I do now is basically exactly what he did in all the classes that I took with him. He publishes lecture notes, but and his lectures sort of follow the pattern or the organization of those lecture notes. But primarily in his lectures, he just demonstrates. He doesn't have dense slide decks or anything like that. And I guess I found it really effective because now I do the same thing.
Yeah. I took CS 290 web dev with him last term, and honestly, yeah, like everyone hyped him up to be this like crazy teacher. He's like super goated, and honestly, he like fit the description. It was all that, it was a lot of like he didn't have any slides. It was just like him coding straight up in VS Code, and he was just doing all of it. And then he had like the Star Wars references and stuff too. It was really entertaining to just pull up the class. Yeah,
my friends would always, after I took a class with him, some of my friends hadn't yet, and they asked me to describe him. And I think the way that I always describe the way he teaches is that he never says anything that doesn't make sense. Like everything he says just makes sense the first time he says it. And I think that's partly because of the demonstration aspect. Like he says it and he shows you. Yeah. It just immediately clicks. Yeah. And I thought that was powerful.
And like, part of me wasn't sure if this was like, because 290 it shouldn't be like one of the more difficult classes in terms of like this field. Like, of course, the weed out classes are like CS 162 and then computer assembly, like those ones are the more difficult ones, so I can see people struggling with that. But if you take an already kind of introductory level class and then put a really, really good professor behind it, I feel like that can just motivate people further to get into a field. Yeah, you know.
I don't know about the weed out stuff. I can't officially call CS 162 a weed out course, but I understand.
That's what I've heard, but
I understand the subject. I always say, it's my philosophy that there should be no weed out courses because my goal is not to get rid of students; it's to help students succeed. But yes, there are definitely some courses that are
tougher classes. Would you say that? So, like, what was your experience teaching 162? I guess.
So I actually first taught. Okay, so in 2017, I started as a student, and I took CS 160. Which nowadays people don't know what CS 160 is because I don't even know if we teach it online anymore. I think we've just basically discontinued the course. CS 160 was like very introductory. Some sections didn't even write code. After that, you take CS 161, which is still offered online, like through eCampus. But now on-campus students go through the Engineering Plus series, primarily instead. So Engineering 103 kind of takes on the role that CS 161 used to. And then there was CS 162, of course. And so when I was an undergrad, I was a teaching assistant for the CS16X series. I finished CS 161. I TA'd for it the next term while I was taking CS 162 and so on. And so when I started as an instructor here at OSU, the first class I taught was Engineering 103. The second class I taught was CS 162. At that point, I felt like pretty prepared to teach them because I had basically taught them before as a TA. And so now I was just in a slightly different role. Also, just before I started as an instructor at OSU, for 2 terms, I was an adjunct instructor at Chemeketa Community College. Some students actually here at OSU recognize me from Chemeketa because some of them took my class at Chemeketa. And I taught CS 161 at Chemeketa for a couple of terms. And so I've basically over many, many years built up a lot of experience with these courses in particular. Even at Chemeketa, they're taught very, very similarly for lots of reasons. Like a lot of schools try to, especially in the intro courses, try to make things pretty consistent for transfer students and things like that. And so, Engineering 103, CS 162, I've sort of built up a slow experience with them over a long period of time, which I think was basically necessary because they're hard courses and they have a lot of content. It's a lot of content for students to learn. And if you ever take a course that has a lot of content, you're like, man, this course is really hard. I promise it's hard for the instructor too. Like it's hard to teach that much content. Luckily I had a good foundation that sort of prepared me for it. And so I think I've been keeping my head above the water. I've been surviving.
Yeah. Do you think having that level of experience kind of enabled you to be a more effective teacher?
I would like to think so, yes. Especially, so when I taught at Chemeketa, so I've always heard this advice for people who are just starting to teach. And luckily I heard this advice before I started to teach. And the advice is that if you're about to teach something for the first time, like a new course that you've never taught before, you should use materials that somebody else has already prepared. So somebody who has taught the course in the past, basically because you're still going to be sort of learning the material as you're teaching it. I mean, this is always true. For every teacher, there are 2 learners, as they say. But when I started teaching CS 161 at Chemeketa, my supervisor at the time, Andrew Schuller, He's the program chair. He had all of these like slide decks prepared that he uses to teach. And he has demonstrations that accompany the slide decks. And I started out for those couple of terms, I tried to teach the way that he does, using his materials, like using his slide decks and so on. And very quickly I found that I'm not good at lecturing by slides. Like I'm really not like standing up there and just like, not necessarily reading off of the slides, but like basically reading off of the slides. Like students don't really get a lot out of that. And so you have to have a certain kind of personality, you have to have a certain kind of presentation. And I just didn't have that. And so teaching at Chemeketa gave me the opportunity to realize that and to sort of tailor my teaching style to what made sense for me. And so, yes, absolutely. I think that experience was really important to help sort of prepare me to teach Engineering 103 and then CS 162 here at OSU.
On a similar note to that, we, as a part of our club, when we first came in, this leadership team, we wanted to bring in-person meetings. So Hackathon was like a fully eCampus class or club. And when we brought it online, we were like, okay, let's do these like introductory programming type of club meetings. And then when we started doing that kind of thing where it was like reading off the slides, and we didn't get a lot of like reception. And I feel like a big reason for that was when people show up to clubs, they're not trying to sit through like another 1 hour lecture. Yeah. So we've kind of shifted our perspective a little bit to kind of more demonstrative stuff. Yeah. On the note of, I wanted to jump back to this because you mentioned the Engineering Plus series and how at first it was kind of the 160X series, right?
Right.
What was that kind of evolution like? And because when you studied here, it wasn't a thing. And then now like students go through this 1 year long program where they take like by the end of the year, they're taking 103. Kind of what was that transition like?
That's a good question. I don't know if I'm the best person to ask because I think a lot of that transition happened when I was in my master's program.
Okay.
So I wasn't really engaging with like the intro level CS courses at the time because, all the way through 2020 as a TA, I was like really deep into the CS 16X series.
Right.
And then I think like pretty much right after I graduated in 2020, they started development of Engineering Plus. And in 2020, I think summer 2023 is when I came on as an instructor. And so I was kind of gone during that transitionary phase. But from what I understand, there are a lot of reasons that it was done. One reason is to help engineering students, basically switch majors. So if let's say you're a mechanical engineering student for a year, and then you decide by the end of the year, like you've taken all these mechanical engineering courses and you're like, oh, this isn't what I thought it was going to be. I want to switch. Maybe I want to switch to, my friend is doing electrical engineering and that seems really cool. Maybe I want to switch to electrical engineering. If you've taken a bunch of mechanical engineering courses for your first year and now you're switching to electrical engineering, all of those courses, like the credits aren't going to count toward your new ECE degree path, right? And so the idea of Engineering Plus was we would front load all of like the general engineering content that all engineering students need to know. We would put that all into just like the first year of introductory courses. And so that if you're a year in and you want to switch from mechanical engineering to electrical engineering or something like that, all of those courses that you've taken, the Engineering Plus series, would still apply. And they'd still apply to your new degree path. And that's one of the reasons that I've heard that it was created. I guess there are lots of other reasons as well. But yeah, besides that, I don't really know a whole lot about sort of the the transitionary phase and sort of what went on behind the scenes. Yeah,
I feel like that's a really important thing because a lot of students, like even now, sometimes it's really hard to stick to one thing and like know that I want to do this long term, and that's kind of a scary topic to go into because when you're committing so much time to this, it's like 4 years. And then if I'm going into like masters, then that's another like 2 years possibly. It's always something that kind of can be a tough process. Do you have any advice for students who are like not sure what they want to get into?
Yeah, I'm maybe not the best person to ask this advice for because I've always been interested in computer science from a very young age. But, from what I've heard from a lot of other people who have like switched careers, I don't think it's as hard as people think it is. If you have a mathematics degree, like a bachelor's of science in mathematics or something like that, and you work in the mathematics industry for 6 years or something like that, and then you want to switch to computer science, you can do that. Like people do that all the time. And you don't necessarily have to go back and get a computer science degree. You might be able to find some sort of transitionary job where you're doing like, I don't know, like analytical engineering or something like that. And then you slowly transition into like more of a computer science role and then eventually like a software engineering role. You don't even necessarily have to go back and get a computer science degree. Lots of times, like just the experience on your resume is enough to land you the next job. And so I guess my advice is that 4 years might sound like a lot of time, and it might seem scary of like, what if in the end I end up doing something else entirely? But 4 years is really not as long as you think. And also, even if in the end of at the end of those 4 years you decide to do something a little bit different, that doesn't necessarily mean that everything you've done for the last 4 years was a waste.
Yeah.
You can still apply it. Yeah.
I guess on the flip side, let's say there's a student who's like, I'm locked in. Like, I know I want to do CS.
Yeah.
Do you have any tips for that kind of student and how they should approach doing it?
Yeah. Go into it like hard, like, and like enjoy college too, like don't do too much work, all work, no play, don't do that. Enjoy college. But take all the opportunities that you can, join as many clubs as you can. Do hackathons, do coding competitions, seek out internships, all of those things, especially nowadays. It may be in part with like, there was a tech bubble that appeared during the pandemic and then it kind of bursted and big tech laid off a bunch of employees and so on. And so right now the job market for computer science is pretty competitive. And so I often tell students that like a degree in computer science is not necessarily enough to land you the job. It's enough maybe to get you get your application through, get you to the first round of interviews, but it's not necessarily enough to get you past those interviews and to get you the job, because there's 1,000 other applicants that are applying for the same job, and one of them is going to be really, really, really qualified. One of them is going to be the student who joined all the clubs, they did all the hackathons, they did all the coding competitions. You want to be that student if you can, like if that's possible for you. And so yes, if you're locked in, then like go in hard. Make sure you do everything, especially do stuff, and I hate to say this, but do stuff that looks good on paper too, because ultimately that's what's going to, look good to the employer, stuff like hackathons and competitions and so on. Yeah. Portfolios, build up a project portfolio. Yeah.
Do you have any tips for like what kind of projects to get started on as students?
Yeah. So I have a lot of CS406 students. Do you know what CS406 is? I'm
not sure what
So the credit number CS406 is basically an opportunity where students can just work on a project and get credits for it.
I think I heard about that one. Yeah.
Yeah. And so there's a couple of ways that it can go. They can approach an instructor or a professor and say like, hey, I have a project that I want to work on. Will you just sort of sponsor the credits and like sort of advise me loosely throughout the process? So that's one way to do it. Or sometimes the instructor or the professor will have a project idea, and a student can say, hey, do you have any projects that I could work on for credits? And they will say, yes, here's a project. So those are kind of the two different ways that it would happen. I always prefer when students come to me and want to do projects for credits, I always prefer that they come up with a project idea, because I think it's really important as you work on projects that you're passionate about it. And so sometimes my students will say, well, what's the best way to come up with a project? And so my advice is there's usually two general ways to come up with a good project. One is you already have a project in mind that like you're passionate about, something that you want to create. So create that thing and you can get credits for it. But then the other thing is maybe there's something that you want to learn. So there's a new framework, like a new software framework that you've heard is really popular. Maybe you haven't interacted with like React or like Tailwind CSS or something like that, and you want to learn how to do that. Maybe because it looks good on a resume, and project portfolios look good on a resume. And so you construct a project around that skill that you want to learn. Maybe if you want to learn Tailwind CSS, then you build a web page that uses Tailwind CSS components or something like that. And so the idea is to kill two birds with one stone, to build the project that looks good on your resume and on your project portfolio, and also gain new skills that also look good on your resume and so on. And so that's my general recommendation. Yeah.
Welcome back to the BeaverHacks Podcast. We're going to be continuing our interview with Alex Guyer. So yeah. We're going to roll? Okay. So yeah, on the note of projects and, finding passion in your work, how do you think students can find that balance between passion and, productivity? Because I know a lot of people can get stuck in that grind set of, I got to just work, get that internship, land that job, but they kind of lose themselves in the process.
Yeah, I mean, I think, and maybe this is the machine learning practitioner in me, but I'm always optimizing. But I think the best strategy is to try to do both at the same time. If you ever find yourself like preparing for an interview or trying to build your resume, add something to your project portfolio, and you're not passionate about what you're doing, like you're not passionate about the skills that you're gaining to put on your resume or the project that you're building to put in your portfolio or the skills that you're learning to prepare for the technical interview, then maybe you're looking at the wrong company, right? Ideally, if you're applying for a company with like the same values as the kinds of things that you're passionate about, like their mission statement, you're passionate about their mission statement, then you should be preparing for that job. And as you prepare for that job, to prepare to interview for the job basically means to prepare to do the job. Ultimately they want to hire people who are ready to do the job. And as you prepare for that job, you should be passionate about that preparation because you're going to be learning the same skills and doing the same kinds of things that you would be doing when you in theory work there. And so yeah, if you ever find yourself just doing work and it just feels like work and there's no passion behind it, maybe look somewhere else. Try to kill two birds with one stone. Yeah, don't treat the passion as like something separate from the skills that you're learning along the way.
Right. Yeah. I think off camera just now we talked about your experience in an internship as well, and how without that passion it kind of didn't feel as productive to what you wanted to do.
Yeah. So for the people who couldn't hear us because we were off camera, I had a 6 month internship here in Corvallis at a survey company. This was back, I think it was between like my second and third years of my bachelor's program or something like that. And so it was a 6 month internship. It started, I think, in the spring and ended at the end of summer. But I think like 3 months in, I finished pretty much like the main project that they wanted me to finish. And then I think they were kind of like, what are we going to do with this kid? And so then they gave me another project. And as I worked on this, it became clear to me that like not only was I not passionate about what I was doing, because I'm not passionate about surveying, and this was a survey company. It wasn't a software engineering company. It was a survey company. They built survey software, and they had in-house software for analyzing survey results and so on. And so I wasn't passionate about this. That became very clear to me. I was kind of just doing work because I was being told to do the work. And it also became apparent to me, especially in these last 3 months of that internship, that even the people telling me to do the work weren't passionate about it. Because this was, by the time we got to the end of it, we showed off the project, and the guy that we built it for was kind of like, yeah, I don't really know if I'm going to use this. And in retrospect, that was just wild to me. It was like I was just being given work to do just for the sake of doing it, basically. And I think that's when I realized that like I'm really passionate about computer science, about software engineering, but only if I get to do something that I want to do, I'm not great at doing something that somebody just told me to do, and I do it because they told me to do it. And I think that's in large part one of the things that led me back into academia, back into instruction, is as an instructor, we have quite a bit of autonomy. It depends on where you're working and so on. You get even more autonomy at like a small community college where you're basically running the entire program, But even here at OSU, even at like a big engineering school, me, even a lowly engineering instructor, computer science instructor, I have a decent amount of autonomy. I can generally teach things the way that I want to teach them. I can teach the things that I'm passionate about. So long as I hit the course-specific student learning outcomes of the course, then I can teach stuff however I want. And I think that's really helped me find that passion again.
Do you think professors having more autonomy can be both beneficial and detrimental to the students' actual learning? Yeah,
I definitely think there's a trade-off. There are pros and cons, especially when if you're talking about a really big course, which basically means an intro course, because these are the courses that every student takes, especially like Engineering Plus, like Engineering 103. Every single engineering student has to take this course, at least the on-campus, Corvallis campus students. It's going to be taught. You can't have one instructor teach that course. You need 20 instructors to teach this course because there's going to be so many sections. If everybody teaches it in like wildly different ways, then that can be problematic for students. And don't get me wrong, there's definitely a lot to be gained from like having different instructors with different perspectives. And so that autonomy is still important. But yeah, we definitely need like ways of standardizing things. I've heard of, in different universities do this in different ways. I've heard of universities where there would be a Bio 101 course where there are 3,000 students, and they divide it into 20 sections. And then each instructor teaches like 3 sections or 2 or 3 sections, something like that. The instructors deliver the material that's prepared by their supervisor. And their supervisor is sort of like the instructor of all instructors. And they're like, the instructor at the top. And so you build this instructor hierarchy. But then there's also more hierarchy because below the instructors who deliver the course materials, who deliver the lectures, there's an army of TAs to do all the grading and lead all the labs and so on. And so like they have like big hierarchies for things like that. There are pros and cons to that as well. But in that scenario, if you're one of the instructors at the bottom delivering the lecture materials, you have much less autonomy. And so, yes, it creates a lot of standardization. It makes everything taught in the exact same way. All the students get basically the same education. There are pros to that. But also, now all of the instructors are basically just doing what they're told. And I guess they could very well run into the same sorts of issues where like maybe it's hard to find passion in their job that I kind of ran into at the end of my internship. Yeah.
And then, without that passion, it can tend to, turn into the reading off the slides kind of situation.
Yeah, absolutely. Yeah.
I want to delve into your research a little bit.
Okay.
If you want to do that, just,
Sure.
Your master's and kind of how you went into machine learning AI. I know those are buzzwords, but maybe we could dive a little deeper into that.
Yeah, sure. So like I said, I was always interested in neural networks since like high school, since I first started about them in high school. I think even in high school, I implemented the code is terrible spaghetti code, but I implemented like a very lightweight, like multi-OR perceptron in C++ or something like that. I re-implemented it in Haskell when I took CS 160 at OSU. And so I was very excited to enter start my master's program and like start formally studying this stuff. And so my thesis, I guess I can talk a little bit about my thesis. And when people talk about AI and ML, like when you hear the word AI and ML, like what are the first things that come to your mind?
In terms of like AI and ML?
Yeah, like in the world, when somebody says like, what do you know about AI and ML?
Like probably like ChatGPT.
Exactly, like ChatGPT, O3, the ARC AGI challenge.
All the stuff that's hype right now,
Yeah, all the stuff that's really hype right now. That is not at all what I studied. And so a lot of people don't understand this, but like AI and ML is so much bigger than what you see in the headlines. Right. And when I say bigger, I mean like so much more, there's much more breadth to it. There's so many like thousands of little niches, so many tens of thousands of open research questions that people are trying to answer. And a lot of them have absolutely nothing to do with large language models. And they have absolutely nothing to do with artificial general intelligence, whatever that word even means. It's kind of lost meaning nowadays. And so what I was studying in my master's program, I started, Tom Dietrich was my major advisor, and he brought me onto this project. I mean, it was part of this DARPA program called Sail On. And it was about open world novelty. But basically we were studying, in large part, this thing called out of distribution detection, and the closely related and arguably the same question, which is open set recognition. And so the easiest way to explain this is in the basic closed set classification setting, maybe let's say in like a vision domain, you have images of dogs and you have images of cats, and you want to be able to train a model to distinguish the two. So you presented an image and you want it to say, I'm confident that that's a dog if it's a dog, or if it's a cat, you want it to say, I'm confident that it's a cat. And so that's like the basic closed set classification problem. Out of distribution detection, and I guess similarly open set recognition, extends the problem. And so it says, what if you've trained it on dogs and cats? So it knows what dogs look like, it knows what cats look like, or at least it knows how to distinguish them from each other. And then at test time, you present it with like an image of a zebra or a kangaroo or a horse or something like that. And the goal is to get the model to say, I don't know what that is. Now, because machine learning is just statistics, it's just applied statistics, there are reasons to believe that in some sense it's an impossible problem, right? Because your data that you've fit the model to only contains dogs and cats. And so how can you expect this model to behave in any predictable way when you give it an image belonging to a class of data that it has never seen before? something that's out of distribution, as we say in out of distribution detection. And so it sounds like an impossible problem. But what people found over and over again, this was really confirmed in a paper that came out of Andrew Zisserman's lab at Oxford in 2021. What people found is that if you train just a closed set classifier, like one of these deep vision models, like a convolutional neural network or a vision transformer or something like that, and you train it to just classify dogs and cats, at test time, if you give it a picture of a zebra, it will pretty predictably or pretty consistently, not always, but pretty consistently, it will be very unconfident in its outputs. It's only capable of outputting dog or cat, and some confidence associated with its prediction, but pretty consistently, if you give it something that isn't a dog or a cat, it will be unconfident. And that's a really useful property for out of distribution detection, because you can basically just ask the model, is this a dog or a cat? And if it says, I don't know, 50-50, then maybe there's a good chance that it's actually something else. Maybe it's a zebra or a horse. Even though your model isn't capable of telling you that, you can sort of infer that from from how your model behaves.
So it's not fully telling you it's not a dog or cat, but
right.
It's just saying I'm not 100% sure on
right.
this.
Basically, okay. You're asking it, is this a dog or a cat?
Yeah.
And it's not actually either of those things, but that's what you're asking it.
Right.
So that's the question that it answers. But when it answers that question, it says 50-50.
Right.
And that can be helpful if it actually isn't a dog or a cat. Right. It could just be that your model's bad and it's clearly a dog and it doesn't really know whether it's a dog or a cat. That can obviously happen as well. But either way, people wanted to know why this is the case, or at least Tom and I wanted to know why are these models working in this way? This is a very useful property, but from a theoretical level, from theory of statistics, why does this work? Why are our models behaving in a nice way on data that they've never seen before? And so that's what we studied. My thesis was around this thing that Tom coined, the familiarity hypothesis. And the very basic idea is that when you train these models to distinguish dogs and cats, they're not really learning what is a dog or what is a cat. They're really learning to detect visual cues that help distinguish dogs from cats. And so maybe cats have whiskers and dogs have long snouts or something like that. And so maybe the model learns to detect whiskers and it learns to detect long snouts. And so it learns a couple of different, let's say a convolutional neural network, it learns a couple different sets of convolutional filters to detect these different kinds of features. And when a filter triggers, activates strongly, because there are whiskers in the image or something, it generates high magnitude activations, which then go through ReLU activation functions and so on. And so you end up with strong positive activations coming out of this filter to say there are whiskers in this image. And then there's another filter that will generate strong positive activations if there's a long snout in the image. And so you get these activations propagate to near the end of the network, like the penultimate layer, and then you finally got this logit layer that basically just weights these activations, and it computes a weighted average or a weighted sum. And so it says if there are all of these activations that sort of correspond to the cat class, visual cues that are common in cats but not dogs, then those will all be added together and it will give you a high response for cat. If the dog ones are present, you'll get a high response for dog. If you presented an image of a sea lion, out of distribution at test time, maybe there are whiskers, so there are high activations for the cat class, but maybe there's also a long snout, so there's high activations for the dog class as well. And so you get all these high activations for both classes, and then when they get fed through the logit layer, they kind of cancel each other out because the weights for the cat cues toward the dog class are negative, and the weights for the dog cues toward the dog class are positive. And so they cancel each other out, and you end up with really low logits. And if you have low logits, when it gets fed through the softmax layer at the end, you end up with really low confident predictions. So that's where you get your 50-50 guess.
Oh, okay.
Yeah, and so we did a really complicated analysis for arguably a really simple and intuitive idea, which is just that if it sees a combination of different things from different classes, they cancel each other out. And if it doesn't see any features from any of the classes, then the logits are low for a different reason, but still low. And so that's effectively why it works. And so we called it the familiarity hypothesis because the idea is that when you show it the picture of the sea lion, it's not the presence of a sea lion that causes the model to be unconfident in its prediction. it's the absence of a dog and all of the dog cues, and it's the absence of the cat and all the cat cues, or maybe there are some dog cues and some cat cues, but it's absence of like a common pattern, right? And so it's the absence of the familiarity that causes your model to be unconfident in its outputs. And so those were kind of the insights that we drew from my thesis.
And if it's like both, then it can't be one or
Right.
the other.
Yeah, exactly.
Right?
Yeah.
Okay. That's really interesting. I never really even like thought about that aspect of it.
Yeah, and you can draw a lot of insights from it. I mean, it suggests that, since your model is only learning features that are helpful for distinguishing dogs from cats, because that's what you train it to do, if you want it to be more robust, if you want it to learn more features so that it can like maybe even build, even in an earlier layer, build like unique representations for out of distribution things, you want it to learn more features, maybe you could, for example, like train it on more classes. So even if your original goal is just to distinguish dogs from cats, you could add in 10 other classes to sort of like fine tune its representations and get it to pick up on more cues that are necessary, not just for distinguishing dogs from cats, but also dogs from some of these other things. And it turns out, so we call these auxiliary classes, it turns out with auxiliary class training, your model ends up being better at closed set classification and better at out of distribution detection, which is pretty cool. But again, not really a new finding. But I think it sort of helped explain what people already understood, right?
So how do you think those kinds of ideas have kind of come into the mainstream with?
I don't think they have. I think they should, but I don't think they really have. Like when people talk about AI and ML, they talk about O3, they talk about ChatGPT.
Right.
They talk about these models that are trained on everything, right? My background, like my thesis, the entire idea of my research was you're not allowed to train on certain data. If you train on a sea lion, it's not out of distribution anymore. And so you're not doing out of distribution detection. To do out of distribution detection, there have to be classes of data that you haven't trained on, classes of data that the model hasn't seen. And then at test time, you want it to behave in a certain way on that data. The OpenAI's like sort of their business model and like their general strategy toward AI is train on everything.
Just take as much data and just
build a foundation model that has seen everything that there is to see in the world. So that there is no out of distribution. There are no anomalies. It has seen everything. Everything can be seen as like an interpolation between two things that it has seen before. And maybe you can do that. Maybe you can see a certain amount of success with that, with an enormous amount of data, an enormous model, a crazy amount of compute. $3,000 per inference and O3 high compute, like is such an insane numbers that most of us can't even fathom how expensive that is. So you can see success there, but it doesn't answer like the more fundamental questions of like, how do we train these small models on small data and still get them to behave in ways that we want them to when they inevitably see data that they haven't seen before? Maybe data that we couldn't train them on because this data didn't exist. Like, many, many years ago, people didn't have cell phones. And so if there was a security camera watching a crosswalk and it analyzed people walking, these people would just be walking with their hands at their sides because they don't have cell phones to look down at. And nowadays, when the security cameras watch people walk across a crosswalk, people are often looking down at their phones as they walk. And that's like a different animation. And so if you're training models to classify things that are happening in a scene and you train them on data from 30 years ago from security cameras that are looking at crosswalks, they're going to see people doing very different actions and behaving in very different ways. And so new data appears. How do you accommodate that new data if you don't know how to do out of distribution detection? And so I definitely think these kinds of things, like building like robust AI that's robust to stuff that it hasn't seen before, stuff that maybe it has seen but very infrequently, and so like class imbalance problems, I definitely think things like that really aren't in the mainstream, and I think they should be. Then again, the mainstream really is just like a very small subset of AI. Like I said, O3, ChatGPT, large language models. The general public, when they hear AI, this is what they think about. But AI is really much, much more than that.
Right.
Yeah.
Do you think the situation is that like the data is so vast and generalized because they're trying to do it at such like a wide scale that we can't get those like specific data sets?
Data collection is definitely a problem.
Yeah.
I mean, the entire idea of anomalies is that they're rare.
Yeah.
Right. So if you're trying to be good at anomaly detection, if your strategy is to just train on anomalies, like try to manifest all of the anomalies that you might encounter in the real world, feed them into your model during training, that's inevitably going to be a hard problem because anomalies by definition are really rare.
Right.
So in order to get a big set, like a big corpus of them, you need an insane amount of data, or you need like very targeted data collection processes. So you can somehow generate these anomalies predictably. Some anomalies you just can't generate them predictably. Lightning can strike a computer and flip a bit or something and cause weird things to happen. How do you build machines that are robust to that if you can't generate lightning strikes on a day-to-day basis? These kinds of problems are really hard to solve because that data is hard to collect. Those environments are hard to simulate and so on. And so yes, data collection is definitely a problem. I think the main reason that the general public isn't really thinking about these kinds of things with respect to AI is really just about marketing and funding. And OpenAI's entire business model is about being able to answer the question, if I were an investor and I approached AI and I said, I have $5 trillion to give you, and you can use this to train a model. How big of a model can you train, and what will its test performance be? They can answer that question. They can actually answer that question. And that's pretty crazy that they can answer that question because these are such big numbers. It's crazy that they can make predictions and correct predictions involving these big numbers. But they've done all this research in neural scaling laws and whatnot that they can answer these questions. And so they're operating on extremely high budgets. And so they better be getting a lot of attention from the media and attention from investors. Otherwise, they wouldn't be able to operate on these high budgets. And so it shouldn't be surprising that that they get all the media attention. That's the stuff that generates the headlines. That's the stuff that people know about.
Right.
Yeah.
Yeah. Man, I look-y never had that perspective on it either. I mean, maybe because I'm just getting into it. I'm just barely. All I know is I'm just taking the AI track just taking I'm taking linear algebra this term.
Oh, very good.
Just getting just starting into it. But I feel just seeing that, the fact that everything I know about it and everything I've seen is just such a small subset of what the actual thing is. It
was wild to me too. When I took AI, intro to AI here at OSU with Professor Rebecca Hutchinson, in I think this was 2020, something like this, and we learned about graph search algorithms and minimax. I was like, wow, this is not what I thought AI was. And that blew my mind that AI is so much more than what a lot of us think it is, because it's, it's a buzzword.
In terms of, I guess, maybe people trying to get into AI like myself, do you have any advice for kind of what I should focus on, or what people should kind of put their focus? Because there's a lot of buzz now, and then it's really easy to just be I'm doing AI, and where should people put their focus, I guess?
It depends on what you want to do in AI, because it's such a big thing. If you want to work on large language models, and if you want to work on the ARC AGI challenge or things like that, you'll probably need a lot of the same foundational knowledge as you would for a lot of other parts of AI research. But the deeper knowledge is going to be very different, a very different subset. And so if you're just now looking into getting into AI and you don't know a whole lot about it, I would definitely start with the fundamentals. So linear algebra, super, super important. I would honestly take some vector calculus classes or something like that. Lots of statistics classes, things like that. Once you've covered a lot of those foundational topics, then you can start to maybe pick a branch, and you don't have to pick one, of course. But I would maybe dive into some of the literature. Of course, we have a lot of great AI classes here at OSU. We've got Intro to AI. We've got some deep learning classes. We offer them at undergraduate levels. We offer them at graduate levels. And so, start with the foundational stuff. And then once you've got an idea of the basics, then maybe start to take it from there. Yeah.
Do you think the idea of large language models is kind of overhyped in a sense where people say that's where the money's at, that's where you should kind of be focusing, and if you take the traditional CS route, you're going to be working at McDonald's, once you graduate. And people are saying the shift is happening where you got to be focusing on AI. But is it really the large language model aspect that's kind of where the focus is right now, or are there other areas that you can focus on in terms of?
Well, when people talk about as a software engineer, you need to know about AI, otherwise you're going to end up at McDonald's. I think they are generally talking about large language models. And the reason for that is that as software engineers, we write code, and code is just language. We're just expressing an algorithm in a language that maybe a computer can understand. But it's ultimately just one big language task. That's like our entire job. And so large language models can definitely help with language tasks, right? They're very impressive. They can definitely take like routine coding tasks and basically just do them for you. They're very good at consuming APIs. They know, they've explored the internet, GitHub Copilot, cloud, things like that. They've explored a lot of like even private GitHub repositories, and they know how to interface with even a relatively niche API that most developers would never need to interface with. And so you find yourself needing to write software that interfaces with this API. You can ask the LLM to do it for you, and it will do it. It might make a few mistakes, so you're going to need to like very carefully vet everything that it outputs, but it'll do it. And so the point is, they're tools, and they're useful tools in the same way that an IDE, like VS Code and all of its cool NuGet packages and its debuggers and its code refactoring and code generation tools, just as those are all tools that can make you a more efficient developer, so are large language models. And so I think people should view these things as tools that you need to know how to use to be a more efficient developer, to be better at your job.
So essentially tools that you need to know how to use instead of some crazy Terminator robot that's going to
it's not going to do your job for you.
Yeah.
It's never going to do your job for you. Yeah, you definitely need to know how to prompt it, and you definitely need to very carefully vet everything that it outputs, because these things, even in routine tasks, these things make mistakes all the time.
Yeah.
If I asked GitHub Copilot to solve a certain problem that was like a sort of complicated problem, but with maybe there's a simple design pattern that solves the problem, and it follows like a class of problems where this design pattern is very commonly applied to these kinds of problems. ChatGPT or GitHub Copilot probably isn't going to realize that there's a design pattern that already exists to solve this problem. It's just going to do whatever it thinks makes sense to solve the problem. And so you're going to end up with a lot of not very good code. But if you, the developer, know there's a certain design pattern that I can use to solve this problem, maybe the template method pattern or something like that, if you then prompt GitHub Copilot, apply the template method pattern to solve this problem, it will do that. And it knows what the template method pattern is if you tell it to apply it. But you need to know how to tell it to apply that pattern. Otherwise, it will generate a lot of really bad code that's hard to maintain. Even GitHub Copilot is bad at maintaining its own code. Yeah.
Well, thank you so much for coming on the show. Everyone, this is Professor Alex Guyer. He's going to be teaching 103, 162, and 374. Be sure to stay on the lookout and definitely consider taking one of his classes, because speaking from experience, they're a really good time.
Thank you. Thank you for having me. Warning, I've never taught 374 before, or 372. I've never taught that before. I'll be teaching it next term. So we'll see how it goes.
Fingers crossed.
Yeah. I'll be flying by the seat of my pants.
Thanks for coming on.
Thank you.